Okay, this is Math 1090, Section 3.1 on inequalities. Okay, so when learning about the domain and range of a function in Chapter 1, we discussed inequalities and used set builder and interval notation to describe them. In this section, we will explore how to solve linear and absolute value inequalities in one variable. Okay. The process is very similar to solving equations, but instead of the solutions being a single value, the solution will be an inequality describing an interval of solutions. Okay, so we're going to get infinite number of solutions to these inequalities. Okay, and why do we care about inequalities? Well, at the end of this chapter, we're going to encounter this class of problems that are very useful in a business setting. And these kinds of problems are called linear programming problems. Okay. Now, don't worry, you don't have to really program a computer or anything to do this stuff. But the thing is it requires us, though, to solve inequalities and to express the problem via inequalities. In fact, not just inequalities in one variable, but often inequalities in several variables. But we're going to start off simple here. We'll talk about inequalities in one variable, but also we're going to look at absolute value notation, absolute value functions, and how that relates to and solve both equations involving absolute values and inequalities as well. Okay, so we have a graph here, or a table, with that gives several examples of an inequality on the left column there, and in the middle column we have the corresponding interval notation and then the corresponding graphical notation. Okay, so the blue symbols all refer to what we call strict inequality. So in this first inequality we have -2 is less than x is less than 2. So what this represents is all the points between -2 and 2, but we don't want to include -2 and 2. So we say this inequality is strict, okay, because we're not including the endpoints of the interval. And we use rounded parentheses to indicate that, okay? And then when we do the graph, we'll often do the rounded parentheses as well. Or sometimes you'll see this notation, you'll see like an open circle drawn at around those points, -2 and 2. Okay. In this next example, we have an inequality, -1 is less than x is less than or equal to 3. So all of the red symbols indicate non-strict inequality. So, and that means it could be less than 3 or equal 3. So we want to include that value in our set of values, that is the solution to some kind of inequality. So in this case, we use a square bracket to indicate points that we want to include in our interval notation. So I'm talking about this piece right here. We use that red square bracket to indicate that we're including the point 3 in our set. And then over here graphically we would use a square bracket at the point 3, or sometimes you'll see a dot that's filled in. So a filled in dot means include that point. Okay, whereas over here we would do an open dot. Okay, the center is not filled in to say don't include -1 or exclude it. Okay, and then we have some more examples here. One important thing is this symbol. This is the union symbol. It's a way of combining intervals. We'll see that for some kinds of inequalities, we need this symbol to say, oh, I want this interval and this interval put together. Okay. So let's start with an exercise. Observe the difference for the following equation and inequation or inequality. Okay, so we have 2x plus 1 equals 7 versus 2x plus 1 is greater than 7. But the solution is the same. You would subtract 1 from both sides of the equation. Well, we do the same thing with the inequation. We subtract 1 from both sides, and we get 2x is greater than 6. And then with the equation, we divide, when we have 2x equals 6, we divide both sides by 2, and we end up with x equals 3. With the inequation or inequality, we end up with x is greater than 3. Okay, so notice that the equation has only one solution, while the inequality has an infinite number of solutions. It's everything on the interval x greater than 3. And you see here they've used a little open circle at the point 3 to indicate let's exclude that from our solution set. Okay. All right, let's do another exercise. Solve the following linear inequality, graph the solution on the number line, and then give the answer in interval notation. So we want to proceed as if that inequality symbol was just an equation symbol. I'm going to add 7 to both sides of this equation, and I end up with negative 6x is less than or equal to, let's see, negative 19 plus 7 will be negative 12. Okay, and here now we come to our first difference with solving inequalities versus equations. And that is, well, imagine this little number line here. I have 0, I have 1, I have 2, I have negative 1 and negative 2. Okay? Now, if I were to put inequalities between these symbols, I would say, well, 1 is less than 2, 0 is less than 1, negative 1 is less than 0, negative 2 is less than negative 1, etc., right? Okay, but notice if I were to multiply every single value on this number line by negative 1, I would get what? This would become, negative 2 would become positive 2, negative 1 would become positive 1, 0 would still stay 0, but 1 would become negative 1, and then 2 would become negative 2. Okay? Now notice if I leave the inequalities pointing in the direction that they're pointing in, right, I get something that's false. Negative 1 is not less than negative 2, and 2 is not less than 1. Okay? So the point is that whenever you solve an inequality by multiplying both sides of it by some negative number, you need to flip the direction of the inequality, because now, notice if I flip the direction of all of these inequalities, then it's now true. 2 is greater than 1, 1 is greater than 0, 0 is greater than negative 1, and so on and so forth. So when I solve this inequality over here, when I divide both sides of the inequality by negative 6, I end up with x is less than or sorry, I made the mistake I wasn't supposed to. X is greater than or equal to negative 12 divided by negative 6, which is equal to 2. So we end up with x is greater than or equal to 2. Okay? It asks us to graph the solution on the number line and then give the answer in interval notation. Okay, so greater than or equal to 2. I'm going to use the dot notation. Okay, and I'll use a fatter marker here to denote. What we'll often do is just kind of shade this in to indicate that portion of the number line. And then interval notation. So interval notation would be 2, infinity. We can't include infinity. It's not even a real number. So, all right. Solve the inequality. Give the answer in interval notation. I'm going to add 1 to both sides. I end up with 3x is less than or equal to 6. Divide both sides of the inequality by 3. Now, 3 is positive, so dividing by 3 doesn't change. I don't have to change the direction. We end up with x is less than or equal to 6 divided by 3, which is 2. and it asks for the answer in interval notation. So interval notation would be less than or equal to 2, so we want to go all the way from negative infinity up to and including 2. Okay. Let's see, next exercise. Leah needs to rent a car while on vacation. The rental company charges $18.95 plus 17 cents for each mile driven. If Leah only has $40 to spend on the car rental, what is the maximum number of miles she can drive? Okay. So it looks to me like we're looking at costs here. We have the fixed cost. It costs her $18.95 just to rent the car for the day, and then 17 cents for each mile. So that's the variable cost, right? It varies depending on how many miles she drives. So our cost function, c of x, would be $18.95, the fixed cost, plus the variable cost, 0.17 times x, because it's 17 cents per mile that she drives, right? So I got to multiply that by x, the number of miles. And here I'm letting x equal miles driven. Okay, so we want to, she has to make sure that her costs are less than $40. In other words, c of x has to be less than 40, which is equivalent to saying $18.95 plus 0.17x is less than 40. Okay. And now I want to solve for x on one side of the inequality, so I'm going to subtract $18.95 from both sides. I think I'll use the calculator to do 40 minus 18.95. Okay, so I want to do 40 minus 18.95. That's 2105. So I'm going to end up with 0.17x is less than 21.05. Now, to solve this inequality, I need to divide both sides of the inequality by that multiplier, 0.17. And what am I going to get? Let's see, let's do 21.05 divided by 0.17. So I'm going to take my previous answer, just hit the divide key, and put in 0.17. Okay, so this is going to be 21.05 divided by 0.17, which is approximately equal to 123.8 miles. So there we go. Certainly if x is less than 123 miles, 123.8 miles, she'll be okay. Okay? All right. Let's see here. Okay, let's see here. You are offered 2 jobs selling furniture. The 2 stores offer the following pay options. What amount of sales would you need to make in order for the job with Carrie's furniture to produce a larger income than the job with Cody's furniture? All right. So Carrie's furniture offers you a job paying a base salary of $18,000 a year plus commission of 8% of your sales, while Cody's furniture offers you a job paying a base salary of $24,000 a year plus a commission of 5% of your sales. So, clearly Cody's base salary of $24,000 is better than Carrie's base salary of $18,000, but Carrie's does offer the better commission. So what we need to figure out is, well, how much do I need to sell each year so that Carrie's furniture will be the better deal for me, right? So let's see here. This is income or revenue, right? So we want to kind of think of this like a revenue, but we don't have. It's kind of like a cost function where we have this fixed piece. We get the base salary, even if we don't make any sales, and then the commission part. We have a variable part to our salary as well, right? So let's see. On the Carrie's side, our pay will be $18,000 plus 8% of sales. So that would be 0.08. Let's let X be the amount in total sales we make. And then in Cody's furniture store, or I guess it's C-O-D-Y, okay. Oh. So at Cody's furniture store, we have what? We get $24,000 a year plus 5%, so plus 0.05 of X. And we want to know when Carrie's furniture will produce a larger income than Cody's. So we want Carrie's to be greater than Cody's. Okay. And now we solve for X, right? I'm going to subtract, to begin solving this inequality, I'm going to subtract 18,000 from both sides. And I end up with, what is going on there? 0.08x is greater than, let's see, 24 minus 18 is going to be 6,000, so 6,000. So 6,000 plus 0.05x. All right. Next, I'm going to subtract 0.05x from both sides of the inequality. 0.08 minus, think of it like pennies, right, or cents. 8 cents minus 5 cents is 3 cents. So we end up with 0.03x is greater than 6,000. All right, that's what we want to solve. So I want to divide both sides of the inequality by 0.03. I think I'll use the calculator again. So I need to do 6,000 divided by 0.03. That is 200,000. So X has to be greater than $200,000. I'll put the symbol back in because remember, well, in this case, X is representing our total sales for the year at either store. Okay, so as long as we sell more than $200,000 in furniture every year, Carrie's furniture store is going to be the better job than Cody's. All right. Okay, next one. Solve the inequality. Give the answer in interval notation. Okay, so this is what we call a compound inequality. And the way you could think of it is two inequalities joined together with the word and. You could think of it as like 1 is less than or equal to negative 6x plus 7. And negative 6x plus 7 is less than 13. Okay. But really the simplest way to solve a compound inequality like this is just to do the same thing to all three parts of the compound inequality when you're solving. So, for example, I'm going to subtract 7 from all three portions of the inequality. So 1 minus 7 yields negative 6. So I get negative 6 is less than or equal to negative 6x, which is less than, let's see, 13 minus 7 is 6. All right. And now I want to isolate x in the middle. So I'm going to divide both inequalities by negative 6. Now remember, when I solve an inequality by multiplying or dividing by a negative number, I need to flip the direction of the inequalities. So when I divide by negative 6, I'm going to end up with negative 6 divided by negative 6 is 1. We'll get 1 is greater than or equal to negative 6x divided by negative 6 is x. And then 6 divided by negative 6 is negative 1, and we flip the inequality. Okay. So that is in inequality notation. What would this interval be in interval notation? Well, usually we go back to our standard same direction as the inequalities between numbers on the number line. So we would typically rewrite this as negative 1 is less than x is less than or equal to 1. Okay? Because this is just a little bit more, we usually read left to right, and this kind of makes more sense if we put the smaller numbers on the left rather than the previous inequality. Okay, and it's easier to now translate this into interval notation because, let's see, I want to exclude negative 1, and I want to go from negative 1 to 1, excluding negative 1, but including 1. So that would be negative 1, and we want to include positive 1. So there's the interval notation. Okay. Next exercise. Solve the inequality. Give the answer in interval notation. Okay. In case you don't believe that what I did was legit, let's just kind of do it out again, but I'm going to break it up into two inequalities. We could do it like this, right? Let me make this bigger. I could break this up into 5 is less than or equal to 3x minus 1 and 3x minus 1 is less than 8. Okay? I want to solve both inequalities at the same time, so I put and in between. I want both of these statements to be true. So let's solve the inequality on the left-hand side. We get, by adding 1 to both sides, I'm going to get 6 is less than or equal to 3x. Upon dividing both sides by 3, I get 6 divided by 3 is 2, so 2 is less than or equal to x. And let's see, over here, I'm going to add 1 to both sides of the inequality, and I get 3x is less than 9. And divide both sides by positive 3, I end up with x is less than 3. So, what do I know? I know x is less than 3, and x is greater than or equal to 2. Now I can combine these two together, and I get what? If I combine these two together, I get 2 is less than or equal to x is less than 3. Okay? Which is the same as I'd get if I do it like I did in the previous example. I'll do that over here. 5 is less than or equal to 3x minus 1 is less than or equal to 8. If I just add 1 to both sides, I get 6 is less than or equal to 3x is less than or equal to 9. Divide everything by 3, I get 2 is less than or equal to x is less than or equal to, oh, hold on, I screwed up. This should have been, these should have been strict inequalities over here. Okay. And, you know, you see we get the same inequality as our solution. It does ask us to give the answer in interval notation, so that would be this. 2, 2, 3. We include 2, but we exclude 3. Okay, let's move on. Okay, now we're going to talk about the absolute value function. This is a very useful function, and the way you should think of it is this is one of our best ways of measuring distance, or how large in magnitude something is. So when we don't care about the sign, whether something is positive or negative, we just want to know, well, how large is it? In other words, how far away from 0 is it? Then that's when we use the absolute value function. Okay, so it's also called the magnitude function because of that. And it is this piecewise defined function. So this definition really here is the key to understanding the absolute value function. The absolute value of x is x if x is greater than or equal to 0. So in other words, you put if the expression inside of the absolute values is positive, then you just get out whatever was in the absolute value expression. If the expression inside is negative, then you have to take the opposite of it. You have then absolute value of x is equal to negative x, right? When x is... Oh, there's a typo here. Sorry. This is wrong. This should be when x is strictly less than 0. That's a typo. I need to fix that. So when your input is negative, then the output of the absolute value function will be the negative of that negative number. So it will be positive or 0, right? You can get 0. As you can see from the graph over here on the right, you can get 0. That the bottom of the V there has a y value of 0. So you can get 0 as an output of this, but you can never get a negative number out of an absolute value function. Okay. So an absolute value equation is of the form absolute value of A equals B, with B greater than or equal to 0. And this will have solutions when A equals B or A equals negative B. Okay, so that's a little confusing. Clearly, if B is less than 0, there will be no solutions. That's true. So the basic idea here is, so when we have an absolute value equation, like such as we have here, 2x minus, the absolute value of 2x minus 6 is equal to 8. Okay? Well, ahead of time, we don't know we don't know the value of x. So we don't know if 2x minus 6 is positive or negative. And depending upon what you put in for x, it could be either or. So we have to take into both possibilities. So if 2x minus, let's assume that 2x minus 6 is positive. In that case, the output of the absolute value function would just be 2x minus 6, right? And we would get, and solving the equation would be tantamount to solving 2x minus 6 equals 8, okay? Easy enough, we can do that. But what if 2x minus 6 is negative? What if it's a negative number? Well, then to get the output of absolute value, we would have to take that number and multiply it by negative 1, as you can see in the definition. So then what I'm going to say here is either that's going to be the case, or if 2x minus 6 is negative, then the output of absolute value will be negative of this entire expression. Okay, so the point is that instead of just getting one solution now to our equation, we're going to get two solutions because there's either of these two possibilities could be true. So now we just simplify both of these expressions. So we have 2x Add 6 to both sides of the equation, we get 2x equals 14. Divide both sides of the equation by 2, and we get x equals 7. I'll use this little double tick mark to indicate I'm just repeating or, the word or. And let's simplify over here. Here we get negative 2x plus 6 equals 8. I'll subtract 6 from both sides, and I get negative 2x equals 2. Divide both sides of the equation by negative 2, and I get x equals 2 divided by negative 2 is negative 1. Okay, so we get this as our solution. X equals 7 or x equals negative 1. So that's it. When you solve absolute value equations, you get two answers. Or no answer, okay? Because we'll see an example of that in just a moment. You can actually get a single result too. That can happen as well. Let's move on to this next exercise. The annual revenue for tracts can be modeled approximately by the formula R equals negative 50 times the absolute value of x minus 10 plus 990, where R is the annual revenue in millions of dollars, and x is the number of years since January 1st, 2010. In what years was, or will be in the future, in what years was the revenue $790 million? Okay, so this is very similar to what we had before. Okay, what we want to do here is we want to know when is the revenue as a function of x equal to 790 million. And we're measuring everything in millions. We're told to keep the output of our function in millions, right? Millions of dollars. So what I want to do is replace this r of x expression with the expression given to us. We want to solve negative 50 times the absolute value of x minus 10 plus 990 equals 790. Okay. So the key thing here is I want to solve this to the point where I just have the absolute value function alone on the left-hand side of the equation. And then I can break it up into two pieces and use the fact that it is a piecewise defined function to break it up. Okay, but before I break it up, I need to isolate the absolute value expression. So I'm going to subtract 990 from both sides. I get negative 50 times the absolute value of x minus 10 is equal to, and 790 minus 990 will be minus 200. Okay. Now I'm going to divide both sides by negative 50. And now this is an equation. I don't have to worry about flipping any directions of inequalities. So when I do that, I get the absolute value of x minus 10 is equal to, let's see, 200 divided by 50 is 4. So I get this. Okay, now that I've solved the equation to a point where I have just the absolute value on the left and some constant number on the right, I can break it up into two pieces. So I get, if x minus 10, if that expression is positive, then the output of the absolute value function will just be that expression, x minus 10. So I get the equation x minus 10 equals 4, or, now assuming that x minus 10 is negative, we have to multiply the entire expression by negative 1. So we do negative, in parentheses, x minus 10 equals 4. Okay, now I have these two equations to solve, which is pretty easy. I get x equals 14, 4, let's see, negative x plus 10 equals 4. So negative x equals negative 6. So x equals 6. So either x equals 14 or x equals 6. There we go. Okay. I want to point out how we could do this, solve this problem graphically. Okay, I think it's always important to kind of understand the interplay between the graphs of functions and the algebraic manipulations that we're doing. Okay, so really what we want to do is know when are these two expressions equal? For what x values will that equation be true, right? The way I can do this on the calculator graphically is, let's see here. What I want to do is I want to graph the left-hand side. So let's put that into a function. Let's see, negative 50 times, okay, the absolute value function, that's in the math menu under num. It's the first one there. Absolute value of, let's see, x minus 10. And now get out of the absolute value bars. Okay, plus 990. And then I'll come down to my second function. This is just the constant function 790. All right. So I'm going to plot both functions and see, okay, well, what x values give the same y values? Where do they cross each other, in other words? Okay, let me figure out some window dimensions that would be good here. So let's go back to the context of the problem. So x here is years since January 2010. So we probably don't care about before 2010. So let's set x min to 0. And x max, let's go 30 years into the future. That seems like a nice round number. Our x scale, measure years in every 5 years, maybe. Okay, what about y min? Let's see. We're going all the way up to, well, I see 990 in the revenue function. Maybe 1,000 or for the max, and let's say 0. Hold on. We want 0 for the min probably, and then maybe 1,000 for the max. What should how far apart should our tick marks be here? Maybe every 100? Okay, and let's graph that. Okay, so the blue graph is the revenue, and the red graph represents a revenue of 790. And if I trace this, I'm going to go up, put my cursor on the red graph there. Let's see here. Let me make this bigger so you can see this. So yeah, when x is, it's using approximate values. So yeah, when x is about 14, we get 790. Okay. And if I come over here, let's see. Yeah, so when x is just over 6, we get 790. Oh, I should be on the blue curve, shouldn't I? Really? I should be on the blue curve. Let's see here. Yeah, so when x is, we get 5.9 there. And just a little over 6, we get just over 790. So yeah, I can trace this absolute value function, and you see, yeah, let's see, 14.09 when y is just under 790 there. Okay, so yeah, it does match our solution. In fact, if you want to be absolutely sure, we could calculate values. So let me hit calc. I want to calculate a value. Let's set x equal to, say, 14. Yep, we get 790 out of the absolute value function, the blue function. Okay, good. Okay, so then, but really the question is asking in what years was the revenue 790. So now we got to remember, okay, year 0 corresponds with the year 2010. And so then year 6 will correspond with 2016. And over here, 14 years in the future, that will be 2010 plus 14 will be 2024. So I think our answer should be the year 2016 and the year 2024. Okay. So in those 2 years, we'll have revenues of 790 million. Okay. Excellent. Okay, now we've seen absolute value equations. Let's look at absolute value inequalities. I'm going to get rid of the calculator for a moment here. So, absolute value inequalities. Like I mentioned at the beginning, these are very important when thinking of magnitude, or how large in magnitude something is, and estimating it. Okay, here's an exercise. Solve the absolute value inequality. The absolute value of x minus 5 is less than or equal to 4. Here we've done it graphically as well. We have the graph of the left-hand side of this inequality is in blue, and the graph of the right-hand side of the inequality is done in the dashed green line. Okay? And we can see from where these two graphs cross at these points that the x value of that coordinate is 1 in that case and 9 in this case. So, but what do we really want? We don't just want these points 1 and 9, do we? And it's a non-strict inequality, so we do want to include these points in our solution set. But really what we want is all the x values where such that this left-hand side expression is less than or equal to 4. In other words, think of both of these as functions, and their outputs are what you get when you evaluate these functions. And so when are the y values of the absolute value function less than or equal to 4? And that's this region here between 1 and 9. And we include the endpoints. So if we were to give this answer in interval notation, we would say the solution set is the interval from 1 to 9. And we could say, just call it a closed interval. A closed interval includes its endpoints, both of them. Okay. Now, how do we solve such a problem, an inequality involving absolute values algebraically, though? So, the key is to think of this in terms of the absolute value function. Remember the definition of absolute value. It's this: the absolute value of x is equal to x when x is positive or 0, and the negative of x when x is negative, or the opposite of x when x is negative. So what I can do is, whenever I have an expression like this, the absolute value of some quantity is less than or equal to some quantity, I can think of this as two expressions. I can think of it, well, what if x minus 5 is positive? Then x minus 5 is less than or equal to 4. But if the x minus 5 expression is negative, then I would have to take the opposite of that expression, and the opposite of that would be negative 1 times, in parentheses, x minus 5, and set that less than or equal to 4. Okay, so And really what I want here is I want the x values that solve both of these inequalities, and so I'm going to put the connective word "and" in between these two inequalities. So now I just go ahead, so I've translated, the point is I've translated this inequality involving an absolute value into what we call a compound inequality. Okay, and I'm going to show you a shortcut way to do this in just a moment. So this is really the long way of doing it, but I think it's good to see both. Okay, so I'm just going to solve both inequalities now and then see what I get. So add 5 to both sides here. I'm going to get x is less than or equal to 9. And here, distribute the negative sign. I get negative x plus 5 is less than or equal to 4. And now I subtract 5 from both sides, and I get negative x is less than or equal to negative 1. And now I'm going to multiply both sides by negative 1. Got to remember to flip the inequality, though. X is greater than or equal to 1. So my solution here is x is less than or equal to 9, and x is greater than or equal to 1. Which we would normally rewrite like this. So I notice I could rewrite this inequality as 1 is less than or equal to x, and then I could combine these two inequalities together by simply saying this: 1 is less than or equal to x, but also x is less than or equal to 9. Okay? So, so there's the solution as an inequality. We could also write it as an interval. The interval would be the closed interval from 1 to 9. Okay? But that's really the long way of doing this. Whenever you have an absolute value inequality like this, and you have the absolute value on the left and some positive number on the right, what we can do is just kind of take a shortcut and just rewrite this as x minus 5 less than or equal to 4, and make it on this side greater than or equal to negative 4. Okay? So you just take this number and put it on both sides of the expression inside the absolute value bars, but on the left you make it negative. That's equivalent to what we just did. Okay, and you'll see we'll get the same solution set here. And now I'm going to just solve this compound inequality by algebraic means like I normally would, but remembering to do the same operation to all three expressions. So first I'm going to add 5 to all three portions here. Negative 4 plus 5 is 1. So I end up with 1 is less than or equal to x is less than or equal to, and then 4 plus 5, of course, is 9. Okay, so see how much faster and easier that was to get to the answer than this long process, right? Okay, so if you have, the point is this. If you have some kind of expression like x minus c, an absolute value, is less than or equal to b, you can then just rewrite this as negative b is less than or equal to x minus c is less than or equal to b, and solve as we normally would algebraically. Okay? So there we go. That's how you solve absolute value inequalities. Okay, now, how do you actually use this in real life? We'll see here in this example, this exercise. Okay, so a 2018 poll reported 73% of students believe that textbooks for school cost too much, with a margin of error of 2%. So this is a pretty common result you get from doing some kind of statistical analysis of some data, right? The margin of error tells us how far the actual value could be from the survey value. So think of it like distance, how far, right? So absolute value is great for measuring distance. Okay, and then this can be described with the inequality x minus 73 in absolute value is less than or equal to 2. Okay, so what this absolute value is telling us, this absolute value of x minus 73 is less than or equal to 2, is saying this. We don't know what the actual percentage of students who believe that textbooks for school cost too much is. We don't know that precisely. Why? Why don't we know it precisely? Well, because we didn't ask all of the students in our population. We just asked some of them. We picked 100. We asked them, and we're kind of saying, okay, this, because we picked the students randomly, and this is getting into ideas from statistics, but as long as you pick your sample set of your population randomly, then yeah, this should be somewhat representative of the actual population. And then in statistics, you learn techniques for putting figuring out the margin of error. Okay, and then we can say, well, we don't know what x is precisely, but we measured it to be 73 in the sample, and we know from statistical means that our margin of error is 2%. So we could be 2% too low, we could be, or 2% too high. Okay? And that can be perfectly encapsulated in this expression. The absolute value of x minus 73 is less than or equal to 2. So if we think of this geometrically, what this expression on the left-hand side is saying, the distance from the true value, from our measured value 73, the distance, absolute value, is less than 2. It's less than or up to 2, equal to 2, right? Okay, so now, well, what is the actual range? What could the true percentage of students who believe that textbook costs are too high be? What range could it be in? Okay, so we want to solve this inequality. So what we do is we transform this into a compound inequality. We just put negative 2 on the left, we put positive 2 on the right, and we use the same symbol. If we have strict inequality, we use strict inequality. If we have non-strict inequality like we have here, we use that. And then we can drop the absolute value bars, and we just take the expression inside the absolute value function and put it in the middle. And now we solve this compound inequality by adding 73 to all three portions of it. And what are we going to get? 2 plus 73 is 75. X minus 73 plus 73, of course, gives us x. And then 73 minus 2 is 71. Okay, and so there we see that in inequality notation, x has to be between 71 and 75, or in interval notation, we would use the closed interval from 71 to 75. Okay, so we don't know for sure what the true percentage of students of the entire population of all students who believe that textbook costs are too high, but it is certainly between 71% and 75%. Okay, one last exercise. Oh, no. Another exercise here. Okay, so with this exercise, notice we don't have just a single absolute value expression on the left-hand side of the inequality. So, but that's okay. We can solve this by doing a few algebraic operations before we break it up into a compound or double inequality. So I'm just going to subtract 4 from both sides. So 26 minus 4 is 22. And now divide both sides by 2. 22 divided by 2 is 11. And now I have a single absolute value expression on the left, and I have a constant on the right. However, notice that the direction of the inequality symbol has changed direction. Okay? So what we want to do here is the same as before, but now we don't want to use the connective and between our compound inequalities. We want to use the connective or. Okay? So if you have something less than a constant, we use we use and as our connective. Okay. But if we have the absolute value of something is greater than some constant, then we use or between as our connective between the expressions we get. So again, we don't know if x plus 7 if it's positive or negative, right? So we take the positive case first. So let's assume x plus 7 is positive. Then the absolute value of x plus 7 is just x plus 7. So we get the inequality x plus 7 is greater than 11. And here's where our connective comes in. So or. Now, the other case would be where x plus 7 is negative, and then the absolute value of that negative number would be, we would take the opposite of x plus 7. And that has to be greater than 11. So we end up with this compound inequality with the connective word or joining them together. We'll see why that's important in a moment. And now I solve these inequalities as I normally would. Subtract 7 from both sides here, and I end up with x is greater than 4, or negative x minus 7 is greater than 11. Negative x is greater than, let's see, add 7 to both sides. I'm going to get 18. So x is, now I got to flip the sign. X is less than negative 18. Okay. So either x is greater than 4 or x is less than negative 18. Okay, let's look at this graphically. I'll put my 0 here, and I'll put 4 here, and negative 18 would be somewhere around here. Okay, so I want greater than 4, and I want strict. So I'll do an open circle, and I'll shade this portion of the line. And then I want, so x is greater than 4 or x is less than negative 18. So we don't want to include 18, so we do an open circle there and shade in everything less than negative 18. Okay. So graphically, that would be our solution set. And in interval notation, this would be from negative infinity to negative 18. Union means or 4 to positive infinity. Okay. So this is kind of the key idea is over here, right? If you have some absolute value is less than a constant, you use the connective and to make your compound inequality. And with when you have an absolute value is greater than some constant, you use or as your connective. All right. Okay, in this next exercise, we're going to see something interesting that can happen. Again, this is going to be one of the or cases, right? But I haven't gotten there yet. First, we've got to simplify this down until we have just a single absolute value expression on one side of the inequality and a constant on the other side. So the first thing I'm going to do is subtract 9 from both sides of this inequality, and I get, let's see here, I get 5 times the absolute value of x plus 3 is greater than, let's see, 4 minus 9, that's negative 5. Okay? Still not quite there yet. I need to divide both sides of this inequality by positive 5. And when I do this, on the left, I get x, absolute value of x plus 3, is, oh, no, I don't need to flip the sign because I'm dividing by positive 5. So negative 5 divided by 5 is negative 1. Okay. And let's see here. At this point, I can really stop. Okay. Why? Because think about this. Remember, the absolute value function always returns a non-negative result, 0 or a positive number. Okay? No matter what I put into the absolute value function, I am guaranteed that its result will be non-negative. Might be 0 or positive, won't be negative. Okay? Now, in other words, no matter what I put in for x, the output of this function will always be 0 or higher. So it will always be greater than negative 1. Okay? So this means that all real numbers satisfy this inequality. Okay? If you don't believe me, let's do it out using the connective, right? Remember, when we have this case, we want to use the or connective. So let's do it out, and we'll see that any number works. Okay? Any number will satisfy the inequality. So what do? I rewrite this as, let's assume x plus 3 is positive, then the absolute value of x plus 3 is going to be just x plus 3. And we get x plus 3 is greater than negative 1. Or, now we assume x plus 3 is negative, and we take the opposite of x plus 3. And that has to be greater than negative 1. Okay. So now we solve both inequalities. We get subtract 3 from both sides. I get x is greater than negative 4. Or here I get negative x minus 3 is greater than negative 1. Add 3 to both sides. I get negative x is greater than negative 1 plus 3 is 2. Divide both sides by negative 1. I get x is less than negative 2. Okay. So let's see here. Let's graph these on a number line. Here's 0, here's negative 2, here's negative 4. So the first one, so remember our solution was x is greater than negative 4, so that would be this portion of the number line, or x is less than negative 2, so that would be this portion of the number line. And notice we've filled in the entire number line. So the answer is R. Any real number is a solution, or in interval notation, the values from negative infinity to positive infinity. All right. And this concludes section 3.1 on inequalities.